talking about Buddhism and science, I'm not going to try to prove that Buddhism is in some way scientific, but rather compare the two as different forms of knowledge. I think one has to be very careful of making claims for forms of ancient philosophy that some are more in accord with the spirit of science than others. For in so many ways, science is such a new thing in the world. And I often find that people who make claims for various religions or philosophies of the ancient world as being scientific actually don't know very much about science. So I think we should start in this sort of discussion asking, what is science? First of all, science is a method of description. If we have a form of this kind, a rather wiggly form, as I've sometimes said, the natural world is full of wiggly forms, and science, in dealing with the natural world, is an attempt to describe them exactly. If we describe this particular form poetically, as distinct from exactly, we might say, well, it's like a flame dancing above the fire, burning gas, or something of that kind. But the interest of science is to describe these forms very precisely indeed. And to do so, it employs a method which is fundamentally like this: to superimpose over the form some very simple, regular pattern in terms of which the form can be described. And what we see here is a system of squares which can be described accurately because they can be numbered up and down. And if we were, for example, to fill in the light gray area, the squares over which the form passes, we should get a rather rough but still approximate formal equivalent of the original figure. But you notice in the top left-hand corner of the screen that where the squares are drawn much more finely, you get a greater approximation to the original figure. In other words, the whole method of scientific description is one of, shall we say, putting things in boxes. Basically, this is the act of classification, of representing the complex forms of the world in terms of simpler, regular forms that we can understand, regular forms that we can count, measure, classify, and so on. And in this way, we get a well-controlled description of physical reality. So you could say that, in a way, science is the art of definition, of getting things down, as we say, in black and white, of assimilating the unknown, the irregular, and the wayward to patterns that are known, regular, and controlled. And basically, this is really the whole operation of that distinctively human activity that we call thought. Because thought is fundamentally classification. And so also science is classification. If you read older works of science, works of, say, natural history and zoology, you will see that the primary concern of the scientist was to classify the various species of nature, the various types of butterflies and insects, the various forms of rocks, the various varieties of plants, and to get them all into classes, like animal, vegetable, mineral, and all their innumerable subdivisions. And so thought fundamentally asks of classes. Is a given natural phenomenon in that class, or is it not in it? The question is always, as we say slangily, is we is or is we ain't? And this method of classification is not only basic to thought, but in a way it's basic to the operation of the human nervous system. For of each one of the neurons that compose our nervous system, it can be said that it has only two states, a state corresponding to yes and a state corresponding to no, like an electric current is either on or off. And in the same way that, for example, the television camera scans a given scene, such as my face, and sends impulses along a wire to the transmitter and then to your set. These impulses are fundamentally of a yes or no character. And the structure of the screen at which you are looking is something like that grid structure which I showed you a moment ago spread over the black flame. And it reinterprets the picture in terms of ever so many little units of on or off, yes or no. So in the same way, the great computer machines which scientists have built to give mechanical equivalents of the human mind use, in most cases, what we call binary arithmetic. That is to say, a number system in which there are simply two numbers, 1 and 2, corresponding approximately to the same duality of yes and no upon which all thought is based, and which is also the basis of classification. When we put, in other words, when we put phenomena into mental boxes, when we class them, the fundamental question is it in this box or is it not in this box? And this is the basic principle of science, which it elaborates in the most marvelously complex ways. And I think we might think about some of these more complex forms. The scientist, as I said, does not simply consider the world in terms of such very simple patterns as the grid or the set of squares drawn over a form which he wants to describe accurately. To go to an opposite extreme, the task of the mathematician, who is fundamental to all science, is really to think up complex patterns. And the pure mathematician doesn't bother his head particularly as to whether the patterns in algebra or geometry or arithmetic with which he's concerned bear any resemblance to events in the real world. For example, we would say that in the real world we live in a space, a physical space, in which there are only three dimensions. There's the dimension of height, of width, and then in perspective we can represent the dimension of depth. And we feel that in the real world, in the physical space with which we're familiar, we can only have three right angles drawn about a point. The right angle between height and width, the right angle between depth and height, and the right angle between depth and width. But, of course, the mathematician can, in theory, think of an infinite number of right angles round this point in a kind of imaginary space that we cannot visualize with our senses. And he can say, for instance, that a line drawn this way is also at right angles to all the other dimensions, and go on and on and on, inventing an apparently fantastic space which has infinitely many dimensions. Now, it may so turn out that this speculation, this construction of a fantastic pattern, does have some actual application to nature. And the mathematical equations which are concerned with spaces of infinitely many dimensions are actually applicable to fluctuations in prices and things of that kind. But this was an entirely unexpected application. So the fundamental task of science is to invent patterns and see in applied science whether these patterns enable us to comprehend the behavior of the physical world. There's another sense in which patterns may be used to explain things. Supposing I draw such a figure as this. And ask the question, what is it? Now, there are various ways of explaining this figure and making what appears to be, at the moment, a sort of nonsensical abstraction, the very sort of thing we run across in the natural world, of making some sense of it. Now, supposing I say that is a drawing of a tree trunk with lopped off branches on it. This immediately, in your mind, makes sense of the picture because it has related it to something with which you're familiar. In another sense, it has classified it. It has given an intelligible pattern to these lines which I scratched out on the board. But supposing we offer another explanation of it and say, it's a bear climbing a tree. Of course, the bear is hidden behind the tree. This gives you an entirely different picture of the same original drawing. And so, in the same way, when the scientist explains various natural phenomena, let's say we see a partial eclipse of the sun. Now, if you are a member of a culture which firmly believes that eclipses of the sun are the result of the sun being eaten up by a dragon, you will see something here corresponding to what you see in this drawing when you say, oh, it's a bear climbing a tree from behind. You will have in your mind's eye a highly complex and elaborate version of what's going on here, something in fact like this. There will be the dragon eating up the sun. Now, you won't perhaps actually visualize that dragon in the same way that when I tell you that this is a bear climbing a tree, you will almost, see the bear behind it. You know, here he is. Almost in your mind's eye, you see that bear. And almost in your mind's eye, if you really believe that a partial eclipse of the sun is caused by a dragon, you will believe that you see the dragon. But on the other hand, if the scientist explains it more simply and says a partial eclipse of the sun is simply caused by the moon crossing the sun, you will have a simple picture like that in your mind's eye. So these are the ways in which the scientist is giving an account of the world. He is assimilating things that we don't know, patterns that we don't understand, to patterns that we do understand. And so the question arises further in exploring what is the function of science, to ask, why do we want to do that? Why do we want to be able to describe the world in terms and in patterns that we can understand? And surely the answer is that if we can interpret the unknown in terms of the known, if we can describe what is going on in the world in regular patterns, we can predict what things are going to do next.